Let's continue. Didn't finish writing up. This is the last corollary that I didn't finish writing, but we're basically done. So we just barely proved the second fundamental theorem of calculus. Just to make quick reference to it over here, what did we show? In short, I'm not putting up all the conditions, but we showed that the derivative of the integral from a to x of some function is equal to f of x. The derivative kind of cancels out the integral, giving us back f of x. That's in short what the last thing that we proved. So we got a bunch of corollaries that fall from that. First corollary. If f from a b to r is continuous, then the integral from x to b, notice now x is the variable changing, so over here we had from a constant to a variable. Here we have a variable to the n constant, b is the right hand end of our integral. So then the integral from x to b of f of t dt, or just some function f, is equal to negative f of x. So it gives us a negative of what this gave us. This gave us f of x. If you do it this way, you're going to get the negative of it. That's what we're going to prove. Or a common way that they say this in calculus courses, if you integrate the other way, it makes your value negative. Well, that's not quite the same thing. Never mind. But here's what we're proving. Okay, so let f be some function from a b to r such that it's continuous. Then what are we looking for? We're looking for this integral. Here's how I'm going to make it show up. I know the integral from a to b of f of t dt is equal to the integral from a to x of the function plus the integral from x to b of the function, right? There's no problem with me splitting it up this way, splitting it at some value x. Good so far? Just split the integral in two at some point x is just some point in between a and b. So we split the integral. Okay, now I'm doing algebra and writing my derivative at the same time, so hopefully I don't lose you again. So I'm saying, notice that we were looking for the derivative of this thing, right? So the derivative of this thing is going to be equal to the derivative of this thing minus this thing. So I'm going to subtract this and put it over here, and then change the order I write my equation. So this is this. This is equal to this minus this. And then I'm doing my derivative at the same time. Follow the algebra there? Okay, now we just take the derivative. Nice and easy. Here we get 0, here we get negative f of x. Anything weird?
Why do you get 0?
It's a constant. It's just a value. It's just a number. Because we know the bounds on this. So this is just some number.
And the derivative of a constant.
Yes, and the derivative of a constant is 0. So the derivative of a constant is 0. This is just a constant. This is just some number. It's not changing. This is changing with x. This is changing with x. So it makes sense that they're going to have a derivative, some function that describes how they're changing. A constant doesn't change with x.
Right.
As you vary x, this is always the same. So its change is 0. So, anything else there weird?
And we're using the first fundamental theorem to get the f of x out of that?
Second, we're using this.
Oh, we're using that. Whoops. Yeah.
The derivative from a to x is just f of x. The derivative, integral. The integral from a to x of some function f is just f of x. So that's just using that to evaluate this. That's just a constant. And then this is what we were trying to evaluate. So this is equal to negative f of x. Anything else that feels like I didn't explain? Okay.
Yeah. Well, in line 3 you have the derivative of that integral, but up in your proof, that's not what you're saying. You're just saying the integral is equal to negative f of x.
That is because I did not write it.
Okay, that
Thank
makes
you.
sense.
Yep, that was just me forgetting to put it in there. That's what we were, because yeah, the integral from x to b of f is not just in terms of f again. All right, anything else I did wrong?
I don't think so.
Okay, let's go to our next definition then. Let f be the integral from a to b of r, or let f from ab to r be integrable. This is just a definition. Pick 2 points, c and d, in there, such that c is less than d. We define, this is now a definition, if we try to integrate backwards, So we try to integrate from the bigger number to the smaller number. We define that to be the negative of going from the smaller to the bigger. And then integrating from a number to itself is 0. That makes pretty intuitive sense. The area under a single point, 0. So just definition, anything weird there?
I mean, no.
Good? Okay, here's what I think is going to be a homework problem for you. I mean, worst case scenario, you just flood through all 6 cases to show that's true, but here's what you're saying. Let f be some integrable function, and let x1, x2, x3 be any 3 points in there. We don't know their order. So we don't know what order they go in. Turns out their order doesn't matter. You can always do this. F of the integral from x1 to x3 is equal to the integral from x1 to x2 plus the integral from x2 to x3. And the way that you handle that is using this definition up here. If it's the case that x2 is smaller than x1, then that's going to be the negative of x1 to x2. So you can always get your points in the order that you want using the negative values. And there's only 6 possible combinations for orders those can be in. Right? So, worst case scenario, 6 ways to show. In all 6 cases, the algebra comes out the same. This is true. Feel like you understand what that's ultimately going to say? Okay, so our next little corollary then is proving that if f from AB to R is continuous, and x naught is some point, should rewrite, let f from some open interval AB to R be continuous, and let x naught be any point in there. Then the derivative from x naught to x of f is equal to f of x for any point in there. Almost saying the same thing, but now we're not requiring us to always start at some start point A in our interval. So notice when we were doing it here, from A to X, this is almost saying the exact same thing, which is why it's just corollary. This is almost saying the exact same thing as this, but this one was on a closed interval from A to B, and it was always going from A to X. This is just picking some point in there and integrating from there to X, and it's still just f of X. So we haven't already proved this, is kind of what I'm trying to stress. So you understand what we're proving and why it's slightly different from what we had already proved? Okay. So, observe that the integral from x naught to x of f is equal to this integral using your homework problem. Your homework problem, I can pick any 3 points in the interval, and this is going to be true. Let me check something really quick. Oh, no, that's right. One point where there might be a slight complication. Notice that a isn't necessarily in this interval. How can I justify doing an integral to a?
Because the order doesn't matter.
Yeah, but notice that a isn't in that interval.
Because when you're taking the integral, the endpoints don't.
The value doesn't depend on the endpoints. Perfect. So that's how we justify putting the a's in there. And then once we put the a's in there, we're also just using this homework problem. That's how we justify this step overall. That make sense? Okay. So now we just take the derivative. So then the derivative from x naught to x, the derivative of this thing is equal to the derivative of this thing plus the derivative of this thing, right? Which, once again, is just f of x. Because x naught is a constant, a is a constant. That one doesn't vary with x. This is the only one that varies with x. So we're done. That one makes sense?
It really doesn't matter where you start. If you take the derivative of an integral from a point to the end point, it's going to be equal to f at the end point.
It's going to be f of the value you're varying to. Yes. Correct. Okay. Our last corollary. Let f be a function from the open interval ab to r. Let f from ab to r be continuous, and let h from c to cd to r such that h is differentiable and the image of f is a subset of the open interval CD. So let's make sure we understand this. F maps from the maybe draw a quick picture over here. So we have AB to f of AB, which is a subset of CD. And f maps like this. So the domain of this function, h, the domain of h contains the image of f. In other words, we're making sure that h composed with f is a function. In short, that's what we're ensuring. Once f spits out something, h can take that thing and use it. Okay. Let me actually make sure I wrote down the conditions of this right. Let I be an open interval, we used AB such that f from I to r is continuous. Let J, that's what I use CD for, be an open interval, and suppose that the function h from CD is differentiable and that... Oh, I did it backwards. Good thing I have my back right there. And that h from C to D is a subset of AB. Okay, so I said that backwards. The image of H is a subset of the domain of F. So F composed with H is defined. So if you do H and then F, your function's still defined. And then fix a point x naught in I in our case was AB. And let x naught in AB. Okay, so I think we got that set up correctly. We have the right givens. Okay, then what are we trying to prove? We're trying to prove that the derivative from x naught to a function that depends on x, instead of just x of f, is equal to f of h of x times h prime of x. This is basically, we're using the chain rule now for differentiating an integral. That's what we're doing. And you'll see that that's ultimately what we use to prove this. You remember what the chain rule is for differentiation?
Yeah.
F composed with h prime is equal to what?
It's f.
We'll say of x. We have something to reference.
It's f prime of h of x
It's f prime of h of x
times h prime of x.
times h prime of x, which is exactly what this right here is going to be. Except for don't reuse f and h because we're not. This isn't the composition we're integrating. I'll show you the composition that we're differentiating. I'll show you the composition that we're differentiating. Maybe come back to point out that after we define two functions. So let's start by letting g of x be this whole function. Notice this function depends on x, right? So let g of x be that whole function. And then let f of x be the integral from x naught to x of f of t dt. So notice f of x does not have the h there. That's the only difference. So we've defined it so that g of x is now equal to capital F composed with h of x.
Right.
That's the way we define it. Okay, now this is what we're taking the derivative of. Right? And that's going to be the same thing as the derivative of this, which is going to be the same thing as the derivative of this. Because that's what g is. So, we're just differentiating. So g prime of x now is f prime of h of x times h prime of x. Right? So then, g prime of x is equal to, what is f prime of h of x? F prime of h of x is plugging in f of x, it's exactly what this is. How can I say this best? Let's write it in terms of the derivative, and then you'll see it better. So the derivative of this is equal to f prime of h of x. Let's just write that out using the actual integral notation. That's the derivative of x naught to some value h of x of f. That's not right because, how can I say that better? Because I need to plug that into its derivative. Here's how I'll say it. We'll find f prime really quick. So let's do that up here, and then we can plug it down here. That'll be the easiest way to do it. So if f of x is equal to this, notice that f prime of x then is equal to what?
F of x.
Little f of x, right? Okay, so now doing the substitution here, I think you'll see it.
Yeah.
So I need to plug h of x into f prime of x, which is f of x. So this is equal to f of h of x, or f prime of h of x, times h prime of x, which is exactly what we were trying to prove.
I'm confused, you said f of h of x, and then you said or f prime of h of x, which is...
Sorry, there's two f's up there, so let me say it again. Let's even just forget what I said and say it one more time from the beginning. So you're good with this step, right? Now what is capital F prime? That is little f.
Okay.
So capital F prime of h of x is the same thing as little f of h of x. And then h prime of x is still h prime of x, and g prime of x is the derivative of g, which was our starting function. So this is still g prime of x.
Okay.
Anything else? Think you got it?
Yeah, I don't know how. If I remember how to use it, but.
Yeah, this one is very weird. Most of our test problems, I think, will be having you calculate integrals by hand. So
I'll probably be using this.
So there'll probably be one problem on the test that requires you to do this. Maybe two. Maybe five. Who knows? Shouldn't limit
How many
myself.
problems are on the test?
I don't know.
Like 5.
But, so that's the end of new material, and there you go. That's analysis 1. Now you're ready to restart it and learn it.